mesure. Ok.
Je suis prêt.
Tu es prêt aussi, toi, David? C'est bon pour l'enregistrement? Ok, super. Donc aujourd'hui, on a le plaisir de recevoir Victor Bonjean, qui est à SISSA et qui a effectué sa thèse pas très loin, entre l'ERMA et l'IAS. Il s'est intéressé au cosmic web, aux grandes structures de l'univers avec des approches de machine learning. Et après avoir passé un an à l'IAS, un an, hein, il me semble, Victor est maintenant en Italie, dans un groupe de data science dont il nous dira peut-être un petit mot, ou pas, on va voir. Et ben merci Victor d'être avec nous. Je te laisse la parole.
Eh bien, merci Philippe de me laisser présenter du coup mon travail ici. So should I switch to English? Yes. Hi everyone. So yeah, I'm now a postdoc at SISSA in a new group of data science created by Alessandro Laio, Sebastian Gold, Roberto Trotta, and Guido Sanguinetti. And the aim of the group is to gather experience in machine learning and applied mathematics in all kind of subjects in science, including astrophysics, cosmology, but also genome studies, a lot of things. So please don't hesitate to ask questions. So I don't see the question from the chat. So maybe Philippe, don't hesitate to interrupt me if there are questions, etc. So I'll talk to you about cosmic web structures, observational cosmology. So I will start by doing a small introduction on the cosmic web and the composition of the universe. So the universe is composed by a network formed by nodes linked by filaments and walls surrounding large void regions. Everything is formed by the skeleton of dark matter, and the baryons in the cosmic web are flowing through the filaments up to the nodes, and so mainly the gas and also the cold gas and stars inside galaxies. My main topics, I was especially interested in the cosmic web structures, so like galaxy clusters, cosmic filaments. So in terms of compositions, for example, in terms of temperature, density of the gas inside cosmic filaments, but also in terms of shapes. For example, the shape of the radial shapes of the galaxy clusters can give us information about the cosmology. During my PhD, I was also interested in galaxy evolution. So principally, as you may know, there are two large types of galaxies, the active and passive one. And I was interested in the quenching, that is a physical process that made active galaxies become passive. And we can, for example, have information on these effects by studying properties like star formation rate or stellar mass of galaxies. And so I played a bit with machine learning to estimate efficiency of those properties in very large surveys of galaxies. And so now what interests me is the coevolution between the galaxy properties and the cosmic web structures, so namely the environmental effects. And so I'm trying to study now the cross-correlation between the galaxy properties and the gas density. And so here I played a bit with deep learning to try to detect properly the Sonia-Zeldovich emission in microwave frequencies. That is the best tracer for the faint gas emission in the faint environments that are cosmic filaments. So I will start with the environmental effects on galaxy properties. So I've prepared several topics, and I will see if I have time to present everything. If I don't, so I will start with this one. So as we know, the environments, especially clusters, plays a very important role in the galaxy evolution. So it's a very non-exhaustive list here, but we have the mergers effect, harassment, the tidal interaction, ram pressure stripping, strangulation, mass quenching, etc. All these processes are directly or indirectly related to the density of the structures the galaxies are in. But also now we know that cosmic filaments play also a role in the galaxy evolution. And ask myself, so can we quantify these effects? And I will try to do it by showing profiles, radial profiles of filaments, showing galaxy over density by galaxy types or galaxy properties radial profiles. And I will use machine learning here to estimate galaxy types properly. So if you don't mind, I'd like to get back to the spectrum of a galaxy. So this is a luminosity as a function of the wavelength for a galaxy. We see the black dots that are the observed points, and the gray line that is the reconstructed spectrum. And we see all the contribution of the different components. So in UV, we have the emission of the O and B stars. So it's a direct tracer of the star formation rate. Then in optical, we see mostly the emission of non-ionizing stars. So a tracer, as they are the most numerous, it's a tracer of the stellar mass. And also in optical, we have the ionizing regions. So for example, H-alpha lines to estimate the star formation rate. And in infrared, we see the re-emission from the dust of the UV photons absorbed by the dust and coming from the O and B stars. So it's an indirect tracer of star formation rate. And so it's a very complex process. For example, Kennicut review. And I will focus on the WISE satellite because it has the relevant wavelengths to observe this kind of properties. And for example, with the two first bands of WISE at 3 and 4 microns, where we see the emission of the non-ionizing stars, so directly related to the stellar mass. And also the W3 and W4 band at 12 and 22 micron, where we see the emission of the dust, and so it's an indirect tracer of the star formation rate. So in the past, there have been several studies to try to correlate the luminosity in the W3 band to the star formation rate, for example, Clever et al. 2014, but this is only done with active galaxies only. And for example, in the right, we see the correlation between the luminosity in W1 and the stellar mass, but this is only up to a redshift of 0.1. So can we find another estimate for all type, another estimators for all type of galaxies, unbiased with WISE magnitude? So I've done it with machine learning. So sorry, I just remove. Okay. Sorry. So I've done it with a random forest algorithm. So a machine learning algorithm needs inputs and outputs in order to perform the training. And so as inputs, I have chosen the WISE infrared data, and as output the star formation rate and the stellar mass. And so more specifically, I have chosen the luminosity in W1 for the stellar mass estimation, the luminosity in W3 for the star formation rate estimation as Clever. I also bring the information of redshifts that I have with the SDSS, come back to that, and also the colors W1 minus W2 and W2 minus W3 that are very efficient to segregate the type of galaxies to allow the machine learning algorithm to understand which type is which type. And for the star formation rates and the stellar mass tracers, I have chosen the data from the SDSS. And so the MPA GHU TR8 catalog from Bichman and Kaufman 2004, which has an estimation of star formation rate from emission line and stellar mass from population synthesis model to fit the spectrum.
Victor, may I interrupt you?
Yes, yes, of course.
So what you take as inputs, it's catalogs, or for the WISE infrared data, it's also the spectrum?
Input is a photometric, it's a catalog, yes, of magnitudes.
Okay.
So I have magnitudes in W1, W3, and colors W1 minus W2 and W2 minus W3. I need the information of the redshift to compute the luminosity. And I use the star formation rate and stellar mass as output.
Okay, thanks.
And so in order to do that, I have done the cross-match between the WISE and SDSS on the area of SDSS. And I have a training sample of 580,000 spectroscopic galaxies that I have divided into a training and a test set. And the idea behind is to apply it to a full sky catalog of photometric redshift, which is called the WISE Cross Supercosmos catalog, which contains 18 million of galaxies in the full sky. So random forest, what it is, it's a very simple algorithm of machine learning, maybe the easiest one to understand. So it's a forest of decisional tree, and what the decisional tree does is just it defines simple rules on the input data, like if else to put threshold, for example, and it minimizes the Gini impurity, that is the probability to belong to a certain class. And so, for example, we'll see, so for the first tape would be, for example, look at the color W2 minus W3, and it places threshold into the two colors to segregate the two populations. And then maybe it will be a threshold on the luminosity in the W3 bands to separate between very star-forming or low star-forming galaxies. And that it learned the different thresholds to apply to the inputs to represent it well the output data. So retrain the algorithm, and we can see the results on the test set, which has not been seen by the network. And this is, for example, the stellar mass estimated with the random forest algorithm compared to the stellar mass from the SDSS. So we see a very correlation. And I have compared here with the formula of Wen et al. Using only the luminosity in W1. And we see the contours of the machine learning, so it's narrow scatter. This is the results on the test set for the star formation rate. So we see here very well the two populations. For highly star-forming galaxies, we see that there's a good correlation, and for the low star-forming galaxies, we see that there is kind of a plateau at the end, because I think it's difficult to estimate star formation rates when there is no star formation rate. And so I've compared here with the formula of Clover using the luminosity in W3. For active galaxies only, which is a color map behind, and then we see the contours of the machine learning for active galaxies in blue, So we see that there is no bias. And to give you an example of the danger to apply the Clever formula for passive galaxies, I have applied it for passive galaxies of this sample, the Clever formula, and we see it is the red contours on the plot. So we don't have such bias and with the machine learning seen on the left. What can be done with machine learning? We can see the importance of the feature in inputs during the training process. So I have performed three training, one to estimate the stellar mass alone, one to estimate the star formation rate alone, and one to estimate both quantity at the same time. So in the first case, we see that the luminosity in W1 is very important and alone to estimate stellar mass as it is expected. For the star formation rate, we see that the luminosity in W3 is relevant as it is expected by Clever et al. 2014, but also the color W2 minus W3 to segregate the two population. And when we estimate both properties at the same time, we see that the color W2 minus W3 and the luminosity in W1 band is enough. So indeed, when we plot the galaxies in this diagram of luminosity in W1 and color, we see that it's very able to segregate populations. And I've shown here the passive galaxies in red and the active galaxies in blue that are very well segregated by only the two properties. And then I have focused on different bias, for example, the bias with respect to redshift or with respect to galaxy types. And so here I show the residual, so the mass estimated with machine learning minus the mass of the SDSS as a function of redshift. And we see that the scatter vary, but we don't see any bias with respect to the redshifts. So it's a good thing. And so in the right, we see the same plot as before, so the stellar mass estimated with machine learning compared to SDSS ones. And we see it for different type of galaxies given by the SDSS spectroscopic data. And so we see that for passive galaxies or active galaxies or even AGN or transitioning galaxies, we don't have any bias with respect to galaxy types. So, so it kind of works properly without any strong bias. And so to use it to show you a bit of application to a concrete science behind, I've applied it to the WISE Cross Supercosmos catalog, so 15 billion sources between 0.1 and 0.3 in redshift. And so I have estimated star formation rate and stellar mass, like in this plot. And then I have divided the galaxy with the passivity, information of the passivity, so the distance to the main sequence of star-forming galaxies, to define star-forming galaxies, transitioning galaxies, and passive galaxies. And for all these catalogs, I have constructed full sky galaxy density maps with the Delaunay tessellation field estimator between 0.1 and 0.3. So in this map, we see very well at low Z that there are artifacts from dust, etc., coming around the galactic center and around the two Magellanic clouds. But we also see at high latitude the large-scale structurations of the galaxies. So the aim was to perform statistical properties of galaxies around filaments. So what do we need? We need a catalog of filaments. And we have one from the SDSS spectroscopic survey. So with the disperse technique, we have created a catalog of 6,000 filaments. And based on the galaxy properties maps I just showed you, I have used the Radfield code to measure directly on the galaxy density maps the profile around the trace of SDSS filaments, masked from known clusters to focus on the emission only of filaments. And so I've derived all the stack profiles along the direction of the filaments. For all filaments, I have a profile, and then I just stack all the profiles to get the mean contribution of the property we want to measure as a function of the distance to the center of the filaments. And so this is what I show here. Here I show the galaxy overdensity, the total galaxy overdensity as a function of the distance to the spine of the filaments for different length of filaments. And so we see that filaments are about 50% more dense inside the core. And this overdensity is relevant up to 10 megaparsec far from the spine of the filaments. Then I have split it in galaxy types, and I have done the same profile for only passive galaxies, only transitioning galaxies, and only active galaxies. And what we see here, it's two regimes where we see very well below 10 megaparsec far from the spine of the filaments, the pre-processing of the galaxies when they enter filamentary structures. So passive density of passive galaxies is higher in filaments than density of transitioning or active galaxies. I also show you now the profile of galaxy properties density. And we see here the gradients of these properties in the core of the filaments. We see, for example, in the left that the stellar mass is 0.1% higher, and the star formation rate is 0.1% lower inside the filament. So we see very well, in a significant way, the pre-processing of galaxies in filamentary structures in another manner. So as a conclusion of this study, I've shown you a machine learning algorithm to estimate the galaxy properties in large surveys, and then I've adapted it and constructed a full sky catalog and density maps. I have stacked around SDSS filaments, and I have confirmed the pre-processing of galaxies in filaments. And now we can wonder what is the link to cosmic web other components, for example, the gas content. And so now I'm interested in knowing why there is this gradient of properties and why there is this pre-processing in filaments. And so in order to do that, we need optimal tracer of the gas in faint environments. So maybe with the Sunyaev-Zaldovich effect. And just to say a word about what I do now in SISSA, I apply this kind of algorithm to know the galaxy properties of galaxy hosts of supernova type 1a to better understand the evolution of the supernova luminosity and its implication in dark energy influence. Sorry. So,
may I ask a question before you move on to that subject?
Yes, of course.
So can you go back a couple of slides before when you're showing the passive, yes, this one.
Yeah.
I'd like to understand this. You look at the passive galaxies are preferentially in the filaments, right?
Yes.
Now, the filaments are the ones which have a lot of gas. So they expect that the accretion rate of gas into these galaxies will be higher, and therefore will form more stars, and they will be active rather than passive. So I'm a bit confused about this result. How do you interpret it?
Yes, but there are also more mergers of galaxies that quench the galaxies. There are also the diffuse gas around structures outside the galaxies is denser and hotter. So maybe there are like round pressure stripping effects, very low effects of the interaction with the hot and diffuse gas inside the filaments.
So it looks like the star formation efficiency in filaments is much lower than, say, galaxies which are in the voids or outside of filaments.
Yes, but this has always been already been shown. Sorry, in other studies. It's not the first time we see this kind of effects, and it's just a confirmation here that we see more passive galaxies inside filaments than active ones.
Right, thanks. And just another technical question. Did you use K corrections? Because I see that you got a redshift of 0.3.
Mm-hmm. So I don't use the K correction, but I used the redshift information. So my guess is that the machine learning algorithm know how to correct from the effect of the redshift based on the redshift directly.
All right, thank you.
You're
welcome. Can I suggest something in relation with David's question? Isn't it possible that it's just an age effect, in the sense that the galaxies inside the filaments are older, and so they have already evolved and left, for some of them, the main sequence, and hence the star formation is lower, and there are more passive galaxies?
Of course, this is also a possibility. This is most likely a mix of everything, every effect, and yes, of course, age is also a dominant effect, as in galaxy clusters. So if there is no other questions, I will continue with the detection of Sunyaev-Zeldovich effects and the hot gas in the cosmic web. So Sunyaev-Zeldovich effect, the spectral distortion of the photon of the cosmic background, which pass through the hot ionized gas in galaxy clusters, and with Thomson effects that are that gain energy, and so the spectrum of the CMB is deviated to the high frequencies. And I have a big of screen, Fred. Okay. And so when we see the difference between the distorted spectrum of CMB with SZ and the CMB, we see this very this spectral signature with a decrease of intensity below 217 gigahertz and an increase of intensity below. And so this SZ effect is quantifiable by one parameter, which is a Compton parameter Y, which depends on the integral of the pressure along the line of sight, so the density times the temperature. And for example, the Planck satellites is very suitable to measure the Sunyaev-Zeldovich effect in the full sky, because of this range of frequency between the 100 gigahertz and 857 gigahertz that encompass well the Sunyaev-Zeldovich effect. So this, sorry, I will move the bar. Okay. So the Sunyaev-Zeldovich effect is dependent of the density of the gas and not the density squared. So it's very relevant to use it to detect less dense region as compared to X-ray emission. And this is the Sunyaev-Zeldovich map constructed from a Planck. We see the northern and the southern hemispheres, and we see the red dots, which are the galaxy clusters. But I show you since the beginning the image of the cosmic web with filaments, etc. And we can wonder where are the less dense structures in this image, and we don't see it very well. But by stacking filaments in a Sunyaev-Zeldovich map or around clusters or around superclusters, we can see that there is statistically the SZ effect in these maps, but hidden in the noise. So the faint signal is here in the data, and we just need to detect it in a maybe different way. So you'll probably wonder why I put these people in my presentation. So this is very well known now. Obviously, these persons are not real. These are taken from thispersondoesn't-exist.com. And they are reconstructed with very complex convolutional neural networks that can encompass very well or detect very tiny features, gradients of image, etc. Very efficient to detect all kinds of objects in very complicated multi-channel images. And so I applied one of this architecture called the UNet. So it's a convolution of maps and then deconvolutions to pass from one image to another image. So it's image regression. And I was wondering, can we learn the SZ signal coming from clusters in Planck data to detect less dense structures? And so in order to do that, I have cut small patches in the 6 frequencies of Planck HFI. And I have, for the same small patch, I have drawn segmentation maps of little circles of 1 at the position of known galaxy clusters. In the first case, I used only Planck clusters, so really massive clusters, to see if it was at least possible to use this kind of networks to recover clusters. And then I have added less massive clusters detected only in opticals and or in X-rays and unseen by Planck to try to push the limits of Planck and of the detections. So I have trained that way a network on the training set on the sky, and then there is a small patch on the sky that is not seen by the networks, and where I do the test set. And in the test set, so the machine learning outputs a sigmoid function. A sigmoid function which is between 0 and 1. And so it's kind of a probability, but more like an index of SZ, let's call it that way. And I show at the bottom left the percentage of recovered clusters on 3 catalogs. So the Planck with redshift, the Planck without redshift, so unconfirmed Planck clusters, and the MCXE, which is a catalog in X-ray. And I show the completeness as a function of this index P. And we see that for an index P of 0.1, we recover 100% of the Planck clusters in the test area, as well as new detections that we see on the right. And we have more than 180 new detections for this case of the index 0.1.
Victor?
Yes.
What about false detections?
Sorry?
What about false detections? You
Yes.
recover all clusters, you say you have new ones, but are the new ones real? And do you have ones that you know are not real?
So here what I call new detections is new detection, not new sources. Of course, inside the 180 clusters, I think there are a lot of contaminations coming from, I don't know, dust or something like that. Here in the test set, what I call new detections is everything we don't know. So I've taken the red mapper, the Planck, and the X-ray clusters from Rosat. And these new detections are not seen by any of these catalogs. So this is really new sources. And I have stacked those sources in the Planck maps and in other maps to see if at least in those sources, some of them are real clusters or not. So here the idea is not to say that I have a catalog of new clusters, etc. I don't know at all. The idea of this study is just to proof of concept to see if those kind of networks can or not detect potential clusters through the Sunyaev-Zeldovich effect. So the answer is yes, because we see that in the test set, we recover the Planck clusters, and we have new detections. And so these detections, I have stacked them in the 6 frequency maps of Planck that encompass the Sunyaev-Zeldovich effect, and in the Milka, the Sunyaev-Zeldovich map from Planck. And so we see that there is a hole in the emissions for the low frequency, and we see well, we see the shape of the spectral Sunyaev-Zeldovich effect in the stacked new detections, and we see a very high SZ emission in the SZ map. So it's reassuring. I think it says that at least some of them are real clusters. I hope so. But of course, I don't know which one are the real one. Does it answer your question, Benoit?
Yes, it does. I will come back to
Okay.
this at the end to ask more questions. But...
Okay. So this is for index parameters of 0.1, as I showed you before. So a lot of detections, but potentially a lot of false detections. And for this threshold of 0.1, I have done just a threshold to detect sources, and I have more than 13,000 detections in the full sky. I show you here the distribution of the sources in the sky, and we don't see any. It's more or less uniform, so it's reassuring. We don't see a lot of artifacts from the dust inside the Milky Way or something like that. And I have stacked this time in the full sky the 13,000 new detections minus the known SZ1 and minus the known one from X-rays and minus the ones known from the optical surveys. And I have stacked them in a lot of maps. So the first one is a Sunyaev-Zeldovich map, and we see an emission in SZ. Then in the 6 frequencies from Planck. And we see several things. We see the hole in the 100 and 153 gigahertz. Then we see also a hole in the high frequencies from 200 to 800 gigahertz. But I have also stacked the iris map. This is which is a map of dust. So we see that the hole we see at high frequencies in Planck is in fact a hole of dust. So it means that we see easily sources that are not in the dust because of course, it's difficult to detect sources when there is a lot of dust. And then I stacked the CMB lensing maps and galaxy density maps from WISE, and stellar mass and star formation rates map, and also the ROSAT map showing the count in X-rays. And so in all these maps, we see evidence of galaxy clusters. So at least there are some in the 13,000 clusters, but we don't know how many. So, but again, it was a more proof of concept study. And so this is all this was in the first step when I just used the Planck clusters in the training process. And then I have focused on some non-structures to see if when I added red mapper from optical clusters and X-ray clusters in the training process, we will detect or not faint SZ emission. And this is the case. For example, we see here the emission around A399 and A401, and I show you the Planck SZ map on the right to compare. And I show also the coma cluster. And so we see in the second model that we recover also the very faint SZ signal coming from the very diffuse gas around the large scale structures. So as a short conclusion, I've shown you an application of deep learning to Planck to extract the SZ effect, including very diffuse components. Of course, now it has to be compared with simulations to know the limits and the completeness of the kind of sources we detect. And this network can be optimized and adapted for any component separation in Planck or other CMB experiments like Siemens Observatory, also to RGB images for Euclid and SST, for example, and any multi-channel data, for example, SKA. So I think I'm running out of time. Just say a few words about my current projects, and then I will go to the conclusion. So now what I do is that I try to use different architecture like this one in parallel to do autonomous multi-component separation in microwave frequencies. So the idea is that in microwave frequencies, the signal is a combination of the CMB, the Sunyaev-Zaldovich emission, and the CIB. If I neglect for now all in red, that is the kinetic Sunyaev-Zaldovich effect and all the foregrounds. And the major issue is here the CIB, because the weights are not known. There is a different CIB in each frequencies. And the idea is to use the modulability of the networks to create a really complicated model, and to so use 4 units in parallel that in inputs take the frequency maps, and in outputs and outputs 4 maps. Let's call it CMB bar, CIB bar, SZ bar, and Z bar, and to use as a loss functions the mean squared error between the reconstructed maps with our model and the real maps. And so it's really preliminary tests that I will show you because I just had the plots yesterday. So it's based on the simulation of microwave frequency maps from WebSky, without noise, without beam, and using the Planck and the Siemens Observatory frequencies from 27 gigahertz to 500 gigahertz. And so I show you here the power spectra of the CMB map and the CMB bar map and the histogram of the maps. The same at the bottom for the CIB maps. So we see it's kind of works well, and we recover well the CIB and the CMB. And this is the case here for the Sunyaev-Zeldovich emission, where I compare in blue the power spectrum of the SZ map from the simulation. In orange, the SZ map recovered with deep learning, and in green, from a standard ILC. And I show, so the deep learning map in SZ has a higher noise, but when we do the cross correlation between those maps and the maps from the web sky simulation, we see that for the case of the orange map, that is a map of deep learning, there is no bias, but for the case of the simple ILC, we have a bias in the signal reconstruction. So, but it's not really fair comparison, because here it's only compared with standard ILC and not state-of-the-art modified ILC that are used now for the case of Planck Sunyaev-Zeldovich map. Well, so I will not talk about this, but we can also use CNN to estimate cluster mass based on microwave frequencies. Like here, we see the plot on the top left. We see that we can recover the mass of the galaxy clusters by using convolutional neural networks. Okay, so as a conclusions, I've shown you various applications of machine learning methods to public surveys and preliminary results, proof of concept study that are promising for applications to next generation of satellites and telescopes, maybe for image regression or faint signal recovery in ACT, SPT, or Simons Observatory, maybe for galaxy properties estimations in Euclid and LSST, and also maybe for detection and classification of sources in SKA. Well, thank you very much.
Thank you, Victor. Some question maybe for Victor?
Yes.
Yes.
So I wanted to come back to your to the work on the SZ detection of stars. It sounds to me like a pretty unusual application of machine learning, in the sense that what you do is you take the sky, cut it into pieces, make it into a learning sample. Sometimes you label the detection of SZ1 or 0. And then once you've trained your network, you say, okay, if the result is not of the trained network, okay, if the result is not 1 or 0, it can be anything in between. And then if you put the threshold at 0.1, you find new sources. If I want it to be nasty, you don't know me, but I'm not so nasty. Because I'm sure that something can be done with this. If I wanted to be nasty, I could tell you. If you had used some algorithm that had told you, this is a 5 sigma detection, and then you had lowered your threshold, you would also have found many other sources with lower statistical significance. And some of them would be real, some of them would be false, and if you stacked them, you would have something.
Of course.
So my question is, because, okay, but my question is, what's next? What can you do in your new detection to try and get rid, well, yeah, sort between the correct one and because that would be the definitive improvement.
Yes, I agree with you. So now, as I said, it's more like for the proof of concept of using this kind of networks applied in microwave frequencies for Sunyaev-Zeldovich effect. So here, yes, I agree with you. It's a weird way of applications of machine learning. And I'd like to see it in the way that it is kind of semi-supervised learning, where we know that in the data, we don't know all the true answers. So we just show a few of them, and we see if it can recover the other ones. I agree with you. Maybe if we take, surely if we take the catalog of Plancke-Z clusters at low signal-to-noise ratio, we have the same kind of results in the stack. But in fact, it was just to show if the new detections were not completely off by one bias.
Yeah. In any case, what's interesting is that you don't devise the detection algorithm. Sorry, my phone is. I take my mic and please go on while.
Yeah. Okay. Okay.
Norma?
Oui. Thank you, Victor. In your first part, perhaps connected also with your second one, which are the new properties of filaments, of new hints you find, if any? I mean, new properties, if any, or some said more than what was already found before. And yes.
So it's related to this kind of plots, right?
Yes, or in general, I mean, if you have more properties on the filaments, correlations between them, about the, I mean, the different size.
So
there are different types of filaments, and so
yes, of course.
do you have a way to I mean, some more to say about that, about these filaments of the cosmic web. And in connection with that is also if you have some said results for density profiles or pressure profiles, for instance, if you check it or verified something of I would like to hear about that.
Okay.
Because so, I mean, I don't think you showed that part.
So what we knew before about galaxy evolution in filaments is that in filaments galaxies are more passive and so less star-forming, more massive, and that was already been shown in the previous papers in several surveys and also in simulations. What
yes,
I show here is that
depends also about the redshift. I mean,
yes, I talked about
galaxies, and
of course.
It's not, and also about what you showed. Sorry, excuse me, about what you showed. The ways to characterize environments and different. I mean, there are different ways. I mean, and that the results also depends on the ways you characterize all that.
Yes, so the ways to characterize, I think it's pretty solid. because so every studies have been done at low redshift, so between 0 and 0.5 maybe, and several algorithms of detections have been applied to the surveys. So one used Disperse, one used T-Rex, one used Nexus, one used Bisou, which are different algorithms which treat environments in the different ways to extract filaments, etc. It was also been performed in several surveys, so it's pretty solid in this way also. What I add here is the quantification, I think. I think for the first time I can tell that galaxies are 0.1% more massive, 0.1% less star-forming, and that the passive galaxies is twice denser than active galaxies inside filaments. So maybe is to use now for the next step these quantifications and compare it with the maybe the profile of density and temperature of the gas inside filaments. And those properties were already been shown also, and I think I show it here. Okay, in the plot here, we see the Soniev-Zeldovich effect, the mean average radial profile of filaments, of the same filaments inside the Soniev-Zeldovich map. So what we see here is a profile of pressure times density. And in my paper, where I show all the study about galaxy properties around filaments, I try to do the link between the fraction of red galaxies and the profile of fraction of red galaxies and the profile of pressure obtained with the Soniev-Zeldovich effect, and I try to compare to other results, etc. So I think this is maybe the next steps to understand better what can be the cause of this preprocessing. I don't know if I answered your question.
Well, I don't want to continue to discuss, but I mean, do you find then do you just concentrate in isothermal? I mean, equilibrium. Do you don't have any departure on that? I mean, it's what you said is very solid or very. I don't see. I mean, it's very. I don't. I am not saying your analysis or on the. On this technique is not solid. I mean, the results of all these ingredients you show, harassment, stripping, strangulation, mass quenching, are in connection with all that, and it's known that there are dependencies. And the pre-processing density of passive galaxies is higher in filaments. I mean, I don't understand that these results are completely conclusive. And we know that in cluster and with Soniev effect Zeldovich, it could be also departure from thermal equilibrium, relativistic effects, and so on. All that should appear also.
Yes, so I don't think we have the statistics and the accuracy of the data now to do the same studies we do in clusters in filaments. So to segregate between models of isothermic or not for the gas in filaments, I'm not sure it's possible to do it now when we see the error bars of the profiles.
Yes, I mean, and more importantly is to cover more redshift. I mean, and there you see
Yes, so maybe with
because
the next.
With this, it's very, very, very strict. I mean, very, very short. I mean, the range of redshift.
Yes, of course, but
To extract more things.
so I think we need more data, and I think that with Euclid or LSST, it will be a good thing to do, and we will see maybe the dependence on redshift of all this quantity.
Jonathan?
Yes, I had just a small question out of
Yes.
curiosity, in the sense that you were mentioning in the very beginning that you were also working about type 1a supernova. So I was wondering what you were doing in this field, and just out of curiosity.
Yes, so the hypothesis for for cosmology with supernova is that the luminosity of supernova type 1a is the same, whatever the redshift, whatever everything. And so that's how we can compute distances, and then we can fit cosmological parameters like omega lambda in the case of supernova. And since 5-8 years, we see that maybe the residual of the fit has a correlation with the galaxy properties of host galaxies of supernova. So we try to think that maybe there is something we don't understand exactly about luminosity of supernova. And we think that maybe it could be related to the dust inside the galaxy hosts that can absorb more or less the light of the supernova. So in fact, the luminosity of supernova depends on the quantity of dust in their galaxy hosts. And so estimate the star formation rate or the stellar mass is a good proxy for the quantity of dust. And so the idea is to correct in a proper way the luminosity of supernova, and try to see what it changes in the estimation of omega lambda.
Okay, thank you.
Benoit, do you want to finish your question?
Well, I was more or less finished. I was just, I think, mentioning that what's interesting in the approach that you showed that is that you don't devise the detection algorithm. You don't need to say this is how you should detect the source. The network learns it by itself.
Yeah.
So what may in the end happen is that indeed he has a better success rate than an algorithm that people would have constructed by themselves, just because it learned a better way to do it. Mm-hmm. that is a real possibility. So that's why maybe in the end it could be really interesting to compare its performance with other classical type of source detections.
Yes, I agree, and so this is why I at the beginning I wanted to use machine learning to do that. Is because, for example, to detect the galaxy clusters in the Planck data, it's a multi-match filter, and so the multi-match filter depends in the frequencies. It's the spectrum of Zeldovich effect that is well known, but in the spatial way, it's a GNFW profile. So if the clusters differ a bit from the GNFW profile, symmetrical, etc., maybe the multi-match filter will not be performant. But if we let the networks learn by itself what is the spatial shape of clusters, maybe it will be more performant, yes. Mm. But yes, it's worth to compare.
Thank you, Victor.
Thank you.
So it's already more than 1 hour. I don't know if anybody else has a question for Victor. Okay, so thank you very much. And we will send some reminders for the next seminar, which are now announced on the website of Minerva. Thank you to all, and see you soon.
Thank you.
Bye.
Merci, au revoir.
Bye.